Next slide, please. Thank you. So as Greg eloquently put it earlier, CLIPS is now real. Here is a picture of the Odysseus lander, the lander for IM-1 in our factory in Houston right before we shipped to the Cape at the beginning of the year. And next slide. So the key takeaway from this is the fact that we're going to start to see, as we've heard from some of the speakers earlier today, multiple CLIPS deliveries every year. And in fact, from an Intuitive Machines perspective, IM-1 landed in February of this year. We have IM-2 next year, later this year, IM-3 next year. And then our plan as a company is to have at least an annual cadence of missions. So I look forward to meetings such as this going forward, where we start to have sessions where we have science talks discussing the science of the data that is fresh data that is being acquired with a regular cadence. Next slide, please. So the first three missions all use Intuitive Machines Nova C lander. It can carry approximately 130 kilograms to anywhere on the moon. However, we have once there is a demand for it, there is the Nova D lander that can go all the way up to 2,500 kilograms. And again, the takeaway from this one is the fact that we do often hear that CLIPS can only take small things to the moon, and that isn't true. We can all the CLIPS providers are engineering companies that we can take what is needed to the moon, much higher masses. Next slide, please. Particularly excited to touch upon the Hopper, which will fly on IM-2. The Hopper is developed from STMD's tipping point. Think of it as a mini lander that gets taken to the surface by a Nova C. It's about 1 meter tall. It can carry 8 kilograms of payload up to about 25 kilometers. It was designed for extreme access, for example, to essentially go where either a rover can't go or to be able to get there much faster. Examples include flying into, for example, a lunar pit to see what's in there, or even going into permanently shattered regions. And indeed, the first Hopper to fly at the end of the year will do multiple hops on Shackleton Ridge, including a constant altitude traverse, and finish with flying into a permanent shattered region and flying back out. We have chosen to put on a couple of science instruments ourselves. One is a neutron spectrometer from Puli Space Systems in Hungary, and the other is a DLR pyrometer for measuring temperature. Next slide, please. Of interest to the community going forward, as Jake touched upon, is we're one of the 3 companies bidding on LTV. Our architecture for LTV uses a primary rover for driving the crew with a certain amount of instrumentation, but then using a trailer system so that we can have specific sort of bespoke trailers depending on what the requirements are. So you can imagine having a science trailer, a resource prospecting trailer, or a drilling trailer, or a resource extraction trailer. And in fact, we envision one LTV supporting multiple trailers in order to maximize efficiency. Next slide, please. So on to IM-1. IM-1 mission, as do most CLIPS deliveries, consists of the NASA payloads that make up the original task order and then the commercial payloads. So you can see the NASA payloads listed here. There were 6 such payloads, many of them related sort of to navigation and technology demonstration. And then below that, you can see that there was roughly a 50-50 split in number. We also had 5 commercial payloads. Next slide. So in order to be a CLIPS provider, you essentially have to develop an entire space program. And so some of the highlights associated with the development of the Nova C, just the top left picture here shows it being horizontally being loaded onto a cargo. It was trucked from Houston to the Cape. Then the middle one is actually Odysseus. You can see the fairings of the Falcon 9 just before it closed. And then the image on the right is our engine. We've developed our own cryogenic LOX methane engine that worked extremely well. We also, key technologies include new fiber wound lineless tanks, which are very light, and also we can pick the exact size that we want, as well as our development of navigation pods for both nav and hazard avoidance. Next slide, please. So just a quick look at how we get there. The one advantage of our engine is it does allow a direct transfer. It only takes 5 days for us to get to the moon after launch. We go into lunar orbit for approximately a day, and then descend to touchdown on the surface. Next slide. Again, some highlights from proving of systems on IM-1. Not insignificant was just, you do all the modeling for vibe, etc. But the lander, survived the Falcon 9 launch environment. The image that we launched just about 1 in the morning on February 15th on the Falcon 9 down at the Cape. The middle photo shows the bottom of Odysseus taken from the second stage of the Falcon 9. And then the right image is actually us returning the favor and taking a picture of that upper stage from one of the wide angle cameras, 170-degree fisheye cameras that we had on the lander. Next slide. Here we have an image just as we're leaving Earth. Part of the reason for showing this, the orange tank is the helium tank, and you can see the Columbia logo. And this wasn't just a marketing ploy, if you like, or an agreement with Columbia. This became a technical sharing.
3 minutes.
Yep. Thank you. And so, we realized that the material they use in their coats is actually extremely interesting as a potential lightweight thermal source. So we actually flew it as a test on a portion of the lander, and they in turn looked at how we do multi-layer TLI and have developed that into their coats. Next slide. We don't use DSN. We made the decision to do our own commercial lunar data network. We have an agreement with radio science dishes around the world, anywhere from 18-meter to the 64-meter down in Australia. And so we buy time on those, and all our data was uplinked and downlinked through those dishes. Next slide. And then hit return, see if the movie works, please. And if it doesn't, okay, oh, there we go. So this is just a collection of images taken during lunar orbit insertion. It's fun to show. Next slide. Image, I'm going to speed up a bit. Image in case there's a question. Image on the way down. Next slide. Another fisheye image just before landing. That crater top right will come into play in a moment. Next slide. So we successfully landed, and as you probably know, we had a problem with the connection with the cable with the laser altimeter, which meant we did come in with more energy than expected. It also meant that we landed, if you go to the next slide, we landed about 2.5 kilometers earlier than expected on a fairly steeper slope than planned, a 12-degree slope of that crater that I pointed out. And then next slide. And so we did, one of the legs did break on landing, and then obviously landing on the 12-degree slope caused the spacecraft to be slightly leaning over. But the important thing is that the bus of the spacecraft was intact. We operated for 6+ days, returning just over 500 megabytes of data from all the payloads. Next slide, last 2 slides. So IM-2 goes at the end of the year. Deborah mentioned this. So this is carrying the Prime 1 drill and mass spec, as well as our Micronova Nokia, dropping off JPL's Lunar Trailblazer, as well as dropping off another rideshare opportunities and a bunch of commercial payloads. And then my last slide, again, just to highlight the fact this is a regular cadence. We have IM-3 going next year with payload from the European Space Agency, the Korean Space Agency, as well as JPL Cardio rovers, and the PRISM Lunar Vertex being done out of JHU APL. And thank you very much.